Thank you, everyone. Thank you for joining. Thank you for participating. Today, we're going to give a webinar on precision maintenance, and we're going to go precisely or more specifically on belt and direct drives. We've heard what you guys have told us the last times. You guys like these rather specific and precise webinars on these various topics. Some of you guys might have been in some of the other precision maintenance webinars that we've given before, and they've been pretty popular. And many of you guys have pointed out that you wanted to see belt and direct drive. So here we are delivering, as many of you have asked. Next slide, please. So before we start with the material, let's start with a bit of a introduction, who we are. My name, Michael Simard Chachua, or if you want to pronounce in French, Michael Simard Chachua, whichever, if you want some challenge. So I've been working for Spartacus for over 5 years at this point. Spartacus is a division of Reliability Solutions, and before we were bought by Reliability Solutions, Spartacus was its own company, and before that we belonged to Laurentide. And throughout that time, I've followed the product more than the company. Bit funny, but that's how it is. And so I've been, Spartacus is a asset performance monitoring platform, and I've been in the domain of deploying it at our customers, importing data, maintenance program, routes, and so on. And I'm really, my expertise is in development of maintenance strategy. So operator routes, lubrication routes, mechanical, vibration, oil analysis. So that's really where my expertise is in, and I've developed maintenance program or deployed Spartacus at over 100 sites at this point. So a lot of different places over just a 5-year time frame. So a lot of work. Nathan is going to be our main presenter and our expert with a lot of years of experience in the domain. Nathan, could you tell us who you are?
You bet. So I'm Nathaniel Woody Wood, and Nathaniel, Nathan, Nate, Woody, those are all probably fine. I don't get too upset about any of it. Woody is obviously a nickname, comes from the last name Wood. 20-something years in the Army, and you're going to get a nickname, and that was a pretty good one to carry on. So I come to Reliability Solution with over 20 years of experience as an aviation maintenance technician, the vast majority of that in the Army on Apache helicopters. While I was there, I got to turn the wrenches as a mechanic or a crew chief, depending on where I was assigned to. I got to tell people to turn the wrenches as a maintenance supervisor. Had the opportunity to tell people to turn the wrenches the correct way when I worked in quality control. And I had the opportunity to tell people to turn wrenches faster when I worked in production control. So with all of that said, when I came to RS, it made what I do now pretty easy. So as the field services manager, I've been with RS about 5 years. I still go on the road, do training and consultant work, but I also work behind the scenes at RS with our own people. Where I kind of specialize is in bridging that gap between kind of the salary and the hourly guys, or the upstairs and the downstairs. Hey, we got this great idea. How do we actually implement it? Or they're never going to let us do that. Well, have you asked yet? Right. So with my experience in quality control and production control, I can kind of usually strike a balance somewhere in there. Since I've been with RS, I've been into baby formula factories, pharmaceutical factories, beet sugar processing facilities, pulp and paper, obviously with RS, frozen potatoes, just about any industry you can think of, we've gone into and helped. At the end of the day, rotating equipment is kind of rotating equipment, and we can usually find a way to work through whatever's ailing you. So, Michael, we ready for the next slide?
Yes, please. So before we actually give you the content and details and all the material in this webinar, I just want to talk about who Reliability Solutions is. Many of you guys already work with us. Some of you guys might have maybe accidentally subscribed to this and ended up here. So I still welcome you here. But I think it's good to do a bit of a recap. So Reliability Solutions, we've been in business for over 2 decades, a while now. So it's been a company for a while, and we've separated our service offering basically into 4 different categories. I'll talk about briefly. The top left is reliability services, one of our biggest domains. So we're going to have lubrication development, hierarchy development, ISO 14224, criticality ranking, master data. So those are all things that we either do for you, do with you, or coach you, train you. It depends what exactly your need is, what your situation is, and what your objectives are. But we have various experts within all those categories. We also do field services. So that's, we send technicians at your plant to do condition-based monitoring, planning, scheduling, often called planners, outage, project management. So all different kinds of experts in those domains. Once again, but mostly for assisting you with that work. On the top right, very hot at the moment is the skills development. Very important. The more as our industry and our domain develops, it becomes more of a skills industry. What skills you have or don't have? Where's the gap? What do I need to know? What I'm lacking? Trying to keep up with the most modern practices, the most up-to-date practices, because we come out of university, we come out of tech schools, and we come with a certain amount of knowledge, and the rest of the knowledge we acquire is at the plants we're working on. But sometimes we're also acquiring bad practices that are really just what the last guy did, and we're just perpetuating this. And these skills and courses that we offer are designed to basically break those habits, give you essentially the proper process. And the webinar that we're giving today is an extract from the precision maintenance that we have, which is an extract in the belt and direct drive. So it's really a very small portion of one of the courses and the domains that we give classes on. And the last bottom right portion is the platforms, the softwares that we offer. We've got 2. The left one, bottom left, is Spartacus. Yeah, I've mentioned that name before. So that's the division that I'm from. It's a platform that's designed for asset health performance monitoring. How is your asset doing? What's the result from lube, oil analysis, vibration, thermography? Basically, the aggregate results of all of that in one platform. If you're interested, I can answer all of those questions. And our latest acquisition is Lubit on the bottom right. So these guys have been there for a few decades as well, been in business for a while, and pioneers when it comes to the precision lubrication. They are true experts in the domain, and they really just help us broaden our portfolio, and with their platform that's specialized exactly in that. So I'm sure you guys will have questions during this webinar. There's a lot of you. There's already 91 in the chat. We will try to take questions. We're gonna take about 3 or 4 questions. Teams has a very nice raise hand technique. I'll be looking at it. I'll try to find a moment to get your question through if possible, if time allows. If time doesn't allow, after an hour goes by, we will stay an extra 30 minutes. So we'll be here an hour 30. So we'll be there an extra 30 minutes. And if you guys are available and want to stay and you have some more precise questions you want to ask us, it will be our pleasure to answer that during that time frame. All right.
Okay.
So the agenda for today is going to be in 6 parts. First is really the introduction. So why precision installation? Why does it matter? Why can't I just, if it runs, it runs, and I'm good with that. You're like, yeah, but you're going to repair it in a couple of months, and you're going to re-repair it a few months later, and you're going to be reinstalling it 3 times in a year instead of doing properly the first time. So that's one of the reasons, many others. And Nathan's going to talk about that. We're going to talk about common installation mistakes. There's a lot of them. They're very impactful. We'll go into the belt drives, direct drives, do a bit, which is going to be the main section, the majority of the presentation today. There's going to be the wrap-up section at the end, just to things you should take back home and maybe your next action or next steps for you. And question and answers as allows. But as I said, we're going to stay 30 minutes after the hour for those of you that can stay with us. And with that, I'm going to hand it off to my colleague Nathan, or Woody, or Nathaniel, and he's going to take it over.
All right. Thank you very much, Mikhail. I appreciate it. So, why precision installation changes everything? I got asked to do this webinar, I don't know, maybe a month ago. I got reached out and it was kind of an idea, or the thought process goes, all right, I speak for 40 hours a week on a book that we hand out that has 120 hours of information in it. And Mikhail wants me to speak for 45 minutes and cover the book. So what do I pull out of that? Well, the things that I pulled out are kind of the common themes we hear in a class, the themes that are frustrating, the mechanics on the floor. And so that's kind of the guidelines behind this webinar. And so the first thing is some common myths, right? So one we hear, belt drives, they're forgiving. They don't have to be aligned as well. The belts are made of rubber. They isolate themselves. That driven machine and that driver can't really talk to each other because we've got that rubber connection between them. And that may look true, but it's not. So misalignment eats belts, misalignment eats shivs or sprockets, depending on what we're talking about, increases belt wear. And the big thing it does is it generates load on that bearing and it increases heat. And we're going to see later that both of those things absolutely just kill the longevity of your machines. This one, that middle one, if it runs, it's lined well enough. And I guess we could say that about just about anything. And I've heard it said about direct drives and belt drives. And, one of the recurring themes we get is, well, it's been running like that forever. Now, it hasn't been running like that forever. At some point, it got worse, and it's going to continue to get worse until it plans your next maintenance event. So one of the things we like to talk about is monitoring equipment so that we can plan the maintenance event when we want to do it instead of when the equipment wants us to do it. And we can do that using vibration, bearing temperatures, percent of slip of your belt drive, and all these things can give you early warning signs. And then that last one, well, Woody, we don't have time for this precision maintenance. We don't have time to get this whole facility into a precision state. Well, right now you probably don't. But you have time to get a couple of your PITAs, your pain in the asset machines, into a better state. So maybe you don't get to the precision state right off the bat, but you make that machine last 6 months longer than it was going to, and that just bought you 6 months of time before your next unplanned shutdown in that case. And the simple fact of the matter is, if you start doing precision maintenance across your facility, you're actually going to get faster at maintenance events, not take longer. So once those machines start going into a precision state, they're easier to work on when they do require a maintenance event. And if we can save 4 to 8 hours of downtime plus the parts cost, that extra 30 to 60 minutes to put a machine into a precision state is well worth the time. So what does a bearing failure actually cost? I think anybody on this call will look at this and go, those are pretty conservative numbers, right? So oftentimes we think about the cost of the bearing and $600 to $2,500. That's average for a bearing. Definitely not on the high end, any stretch of the imagination. Labor, I've got 8 to 16 man hours in there. And what that's accounting for is 4 to 8 hours of production downtime, right? 4 to 8 hours of time to work on this. You got a 2-man crew working on this maintenance event at kind of a minimum. So now we're looking at 8 to 16 man hours. Production downtime, if it took our production down, is 4 to 8 hours, and we'll talk about that a little bit. Collateral damage, when that bearing goes out, oftentimes it takes a lot of other things with it. It takes a mechanical seal with it. It takes, depending on how bad it is, it can take the impeller with it. It can take housings. It can take, worst case scenario, it becomes a safety event. So just as that bearing goes out, you don't really know what other parts it's going to take. And then we all know that everybody will get that next part to us overnight if we pay enough. One of the classes, or one of the stories I tell in class, is about a facility that paid $2,000 more to transport a bearing overnight than the bearing cost. So the bearing was $8,000, their hot shot fee was $10,000, and they were happy to pay it. But if they had done that as a planned maintenance event and had been able to forecast that bearing failure, or better yet, had installed it in a little better state and never had the bearing failure, that would have been a lot of money. So you can see down there, total avoidable cost per event, 80,000 plus, assuming $20,000 an hour in lost production, and your production downtime is only there for 4 hours. So, $80,000, I think, is certainly a realistic number. It can be much more or less, but that's pretty accurate numbers. So what are kind of our most costly installation mistakes? What can we do right here, right now? Just we're out working on a machine. What can we do without doing a precision installation? What are the assembly errors that we can fix? Well, when I walk through facilities, I see machines, and that's what I do. Every place I go offers to give me a tour, and I take every one that I can get. And so we go through, and as I'm walking through, I'm kind of looking at the state of their facility so that I can speak to the state of their machines in the class that week. So if you look at this picture, you can start to see some concerns. Take a few seconds and just kind of look at it and start thinking about stuff like what's wrong here? Is it good enough? I mean, it's all put together. Or do I see some issues? And Erwan, if you could trigger the poll for me, we'll talk about that.
The parts are loosened. Base balls are totally loosened, and the shims we see also like are all misaligned. So it's major problem where it starts. Basically, this looseness cause misalignment and any kind of disbalance what we can test during our condition monitoring, which is not that badly, but already like starting causing the problem. So basically, it's very common case.
Yeah, so accurate. I mean, everything you said is going in line. And as I'm looking at the poll results come in, I'm seeing a lot of people are pointing out squishy foot, and I believe that was Oleg that just spoke, if I looked at the screen correctly. And you called that out. You called out the number of shims. And squishy foot is due to excessive shims. So 100%, yeah, I would agree that squishy foot's a problem here. I've got about 8 people, 21% of the respondents have said it's got an improper key. And I think you're probably correct. We'll talk about correct key length in a little bit, but with just that little bit of key sticking out of the driven side coupling, it makes me think that we didn't get our key calculations correct. So I would certainly say squishy foot or improper key are excellent. Improper hardware. Oleg brought up that it looks like the bolts weren't tightened. I can assure you they are. I tightened those bolts right before I took that picture. What you're seeing there, though, is those soft, cheap stamped washers. So those stamped washers, the thin, flimsy washers, when we torque those, can oftentimes become cupped or bowed, which is what we're seeing right there. And that can cause all sorts of alignment issues. That can cause just, as you're making, especially the horizontal moves, it can pull that machine out of where you're wanting to leave it. And then that last choice, I see we've got one who says it's good enough for who it's for. That would be the only answer that probably we would not go with in reliability solutions in a class, but I put it on there for a reason, because I oftentimes hear stuff like that, right? We get to hear well, it's good enough for who it's for. I can't see it from the house. Those kind of comments, and that's not my job. And we address those in class because the simple fact of the matter is, the way I look at it, good enough for who it's for means it's good enough for my family. I'm at work so that I can pay for my family's way of life. So I want to make sure that what I do at work can continue on. And all of these are very simple things to fix while you're putting a machine back together at 2:00 in the morning.
I've got a question to ask to add to that. For the people on the call here, for those of you that identify that one of these 3 problems might actually be something that you see recur often or common at your plant, can you raise your hand with the Teams tool where you do raise hand? I just want to see how many people look at this and be like, yeah, this is really situations that we see at our plants. Yeah. And everyone, yeah.
Yeah.
So the point that I'm trying to make here is that so many of you see this problem. We know these problems do exist, and yet they still remain. They're still the case. They still appear everywhere all the time. So we really need to find a solution and a methodology to get out of this perpetual issue of just repairing the same way we've done in the past. And that was just the point I wanted to make. And thank you, everyone that answered. You can bring your hand down unless you have a question.
And that's a great addition, Mikhail. I appreciate that. The beauty of this is this is a machine that is set up exactly how it will be set up at the beginning of a class. This is the as found condition for a direct drive machine for our class. And every single one of those problems that we identified in there, the improper key, the improper hardware, the cupped washers, the squishy foot, there was no torque wrench used on those bolts. I know that for a fact. All of that your students will correct in class and take precision readings. Yep, that's a good point, Gene. There is a missing cover on both of those circuit fittings. But those assembliers, that squishy foot, that improper key, that improper hardware, not only are we going to have them fix that in class, we're going to have them take vibration readings between each repair so that they can see what the benefits they got from that. So we get to drive home that kind of, well, it's always been like that, and say, well, we can do better and prove that better actually helps out, right? So mistake number one, soft foot. So soft foot is I go to my favorite sports bar. The Green Bay Packers are playing, and since I live in the Upper Peninsula of Michigan, I'm required by law to root for the Packers, not the Detroit Lions. So I go to my favorite sports bar. I'm there with my 19-year-old son. He can't drink anyhow. I brought him so that he can drive me home. We put our hands down on that high top table. The whole table tips towards me. So I look at my boy and I say, put your elbows on that table and don't move them until the game's over. That way it won't rock back and forth. That's a great solution when you have a 19-year-old son who can just hold the table down for you. Not such a great idea with our machines. And part of the problem with our machines is we look at them and we see that soft foot, but we go, okay, well, when I torque this bolt down, it's going to pull that bolt. It's going to pull that foot down to the base, and we don't have this problem. That's true. And what it does is it distorts the case, right? And you can actually hear that case distortion with a vibe pin or a Monarch examiner. You can loosen up the bolt that has the soft foot, and you can hear that distortion go away during a running soft foot check. So that's huge. We've got to fix that short leg soft foot. And then after we fix short leg soft foot, we can fix angular when the machine's in the very close proximity to its final resting place. And that third one, that squishy foot, we got to do the thing that all of us mechanics like myself hate to do. We might have to clean something. Squishy foot is due to the rust, the corrosion, the product adherence to the bottom of the feet. And, oftentimes I'll hear, well, Woody, we didn't move the motor because we just changed the pump. Right, but how are we going to do a precision alignment on the pump and motor combination if we don't fix the problems that are underneath the feet of the motor? So we need to get that short leg soft foot fixed. And once we're in real close proximity to the final resting place of the machine, we'll go ahead and fix the angular soft foot. How do we correct it? We shim, right? We're going to consolidate those shims. We're going to get them to 4 or less shims while making up the stack we need. We're going to use stainless steel shims only. If you're in a facility that's old enough, that's got, the old hand cut shims or carbon steel shims or brass shims, they need to come out and be replaced with stainless steel shims. And we need to have ideally 3 or less, but not more than 4 shims underneath the foot. And we've got to do that before we attempt alignment. If we don't, what happens is we'll get very close to our final alignment. We start playing that back and forth game. Add a little shim here. Take that shim back out. Add a little back in, take a little back out. And we're just real close, but we can't quite get there. A lot of times that's unresolved soft foot. So another big one is incorrect fits and improperly installed keys. I teach these classes a lot. And I go in, and the number of people that are miking shafts and bearings to make sure that shaft and bearing can live together is very rare in today's industries. It just don't see it a lot. A lot of folks aren't comfortable with a micrometer and don't really understand how critically important these measurements are. So they're measuring, if they are measuring, they're measuring with a digital caliper, which of course is only accurate to the thousandth. And yet we've got bearing books that want us to measure tolerances into the 10,000th because you might have, 6 to 8 10,000ths to play with. So we're going to cover that. Taper locks should be 80% contact between the shaft and the bushing bore, and they should never be lubricated. So that's another one that we see quite a bit is, well, what do we lubricate all our shafts in taper locks? Yep, and we lubricate them probably to make it easier to take them apart. And then the answer to that is, yeah, that's why we do it. And when we start talking about how to correctly install a shiv and why it's important not to use lubricant, it can cause the hub to break or the hardware to break. Also, we're not getting that grip like we're looking for when we put lubricant in there. So one of the things we can do if we're worried about taking it back apart is we can verify that shaft surface finish and verify the fit tolerance to make sure that's all going to go together. Improperly installed keys. Keys are our opportunity to restore some balance where balance was removed. So when we cut those keyways, and I know we don't cut the keyways, we being the industry as a whole, but when those keyways get cut in that motor shaft or that pump shaft or the coupling half or the taper lock, it removes material and it unbalances that shaft and it unbalances that coupling. So one of the things we can do is we can put the correct length key in there that restores as much of that unbalance as we can, restore some balance back to the system. And so we'll cover that. A plus B divided by 2 times 0.95 is our key length formula. And when we see that, we'll see a key that's got full engagement and sticks out a little bit past the hub or the coupling there. And that's kind of one of those quick litmus checks. And then those keys should usually be opposed 180 degrees opposite from each other. That'll restore some balance. On some small shafts, less than an inch in diameter, sometimes 180 isn't the best solution for that. And we can talk about how to identify that, but it's really quite simple. You put them at 180 degrees out, take some vibe readings on those two bearings closest to the coupling halves. And if that's not the right answer, then you move it another clock position in, and you can just kind of continue to field balance that and figure out where it wants to be. But generally on most of the stuff we use in industry, we get greater than 1 inch. 180 degrees is where we want to be. Then the big thing with keys that I'm seeing repeatedly now in industry, just everywhere I go, it seems to run into this problem, is key stock and bar stock are not the same material. Key stock is always oversized, bar stock is always undersized. And if we're using bar stock in the place of key stock, we're not getting the fit that we're supposed to have. And I'll ask that question in class and I'll get, what do you mean they're different? How do we tell the difference? Well, in the book, we talk about some measurements, what it should be. And you'll see the key stock is always at size or slightly oversized. Bar stock should be at size or slightly undersized. Once you know that, it's easy to make sure you're using the right stuff. But so many of our folks don't know that there's a difference between those two. Torque values. This is another huge one. This is such a common mistake. And as an aircraft mechanic, I grew up with torque wrenches being the name of the game. There's no reason that you were ever allowed to not use them. We use them on everything. However, I didn't really understand the reason behind using them. I just knew that I had to use them. And there's kind of this recurring thought in industry today that if I get it tight enough and I don't rip the head off the bolt or rip the threads out of the hole, then it's probably fine. As long as I got to my torque factor and I don't go, I don't break anything, I'll be okay. Well, that over torquing can stretch that bolt into the plastic range. And if you read that bottom bullet in that red highlighted block, it says bolt stretched into the plastic range can vibrate loose over time. Of course, you look at the under torque effects over there on the right-hand side, that bottom bullet, bolts without sufficient tension can vibrate loose over time. And we see that also often. Hey, that bolt's loose, it vibrated loose, go tighten it up more. Well, if it's already been stretched into the plastic range and permanently deformed, you can continue to do that as much as you want, but that bolt is already in the plastic range and is not going to deliver the clamping force it's supposed to. So that's why torque wrenches become so important. And then one of the things that I recommend is if we're using hardware that's less than 1 inch in diameter, make it one-time use. So that hardware that's less than 1 inch in diameter is easier to over torque, easier to stretch into the plastic range just because it's smaller hardware. Certainly when we start putting, as I like to call them, ugga-dugga guns or those Milwaukee impacts on there, we can really torque those. And they're comparatively cheap. 1 inch hardware is comparatively cheap. So replacing it lets me know that I'm using a bolt that's not in the plastic range, that I've got a bolt that can do what it's supposed to do. So best practices, I need to use a calibrated torque wrench. So not only should I be using a torque wrench, I should be using a torque wrench that is correct. I should remove cupped or belled washers. They can cause a hindrance with my alignment, and I can replace those with hardened washers, which are less susceptible to cupping. So once they cup, it can cause that machine to pull itself out of alignment when you're trying to do the alignment. But also when that washer cups, it changes the torque value on that bolt, and then we could have some tension issues. And then I need to follow a sequence. Nobody, I don't think, that's ever worked on anything car-wise would just go around in a circle tightening lug nuts. We all kind of know we need to use a star pattern there, but we forget about crossing that shaft and using a bolt, using a torque pattern there. So
Nathan, somebody pointed out, what about lube bolts prior to torque?
Yep. Yeah, so I see Matt's question. Great one. Yes, lube them, please, especially if they're stainless steel. That stainless steel is susceptible to cold welding or galling. And one of the ways we can prevent that is lubricant. The other way we can prevent that is correct torque. However, if we're going to lubricate bolts prior to torquing, we must account for that reduction in torque setting. So, pocket reference books, there's friction coefficients all over the internet. They're covered in our textbooks. They're covered in the pocket reference book we hand out. I know iEngineer is an app that I keep on my phone. If you have an iPhone, it's a pretty handy, rough guess. It's not exact. But we do need to minimize, or not minimize, but we need to change our torque setting on our torque wrench when we're going to use lubricant, generally by about 25%. But each lubricant's got a different torque setting. So what happens is if we use anti-seize or lubricant on a piece of hardware, but we have it set to the max torque, we will overstretch that bolt. And in some of our classes, we actually use a Skidmore-Willem unit to show that bolt tension and show once that bolt's been stretched into the plastic range, there's no getting it back to doing its job correctly. So yes, 100% use lube on the bolts, but we have to account for that lube when we're doing our torque settings.
Hope that answers your question, Matt.
All right. So when we talk about belt drive, perfect. So when we talk about belt drive, selection and tensioning, selection goes into a lot of things, and the industry is so good with helping you select a belt drive now. Gates has Design Flex Pro, Continental has Make Power, Best Torque will help you out. Theirs is internet based, and you actually have to email and get a username and log in to use their calculator. But they will help you figure out how many belts you need, and all that kind of stuff. Some general things to think about: your standard cross sections. Probably everybody on this call's, familiar with these: A, B, C, D, and E belts. And then, of course, we have our narrow high capacity cross sections, or 3V, 5V, and 8V. And what those allow us to do is put a narrower belt onto a narrower sheave, onto a shorter machine shaft to fit more belts into smaller spaces. How much power we transmit is going to be dependent on how much belt's in contact, so that arc of contact, the belt condition, its velocity, the operating conditions. Is it in a wet environment? Is it covered with product? Is it covered with grease and oil? All of these things are going to check or going to change how it transmits power. So critical rules with belts. One, they're not forgiving. We still have to align them, but always replace belts as a full set. So if we break one belt in a 4-belt set, we should replace all 4 belts. New and used belts are tensioned differently. New and used belts are different lengths. And we should want the belts to be from the same manufacturer, ideally the same lot number or a matched set. Used to be easier to buy matched sets of belts. The power band has kind of made that a little less common, although I've certainly been to places where they have vendors that will still make sure that, if they order 5 belts, they'll order them from the same lot number. So there are folks that will still out there and kind of do match sets for you, but that power band is kind of taken away from the putting 4 individual belts on a pulley. I can put one power band on there. And that makes sure they're all the same length. Belt should be in a cool, dry place. So less than 85 degrees Fahrenheit, less than 70% relative humidity. And that's one of the ones where everybody in the classroom goes, well, Woody, that's never going to happen. They're never going to air condition our storeroom. I'm like, yeah, but if they do, you'll have everybody volunteering to work in the storeroom. And that's pretty common. We don't see a lot of climate-controlled storerooms. Certainly facilities that have a large investment in those static parts and in those assets. They look into it because it is critical to making them last longer. But if I'm not going to do that, then there are some things I can do to help, like follow a strict first in, first out policy. It's very often that we see that new belts get hung on the same peg that the old belts are on, but they get hung in the front. So when I need to go get a belt out of the storeroom, of course, I'm going to grab the one in the front. I'm not going to grab the one in the back. But if you look at it more like the milk section of your grocery store, where when they stock that shelf, they put the new milk in the back and that milk that's about to expire in the front to kind of encourage that to go first. Never hang V-belts on a saddle smaller than the minimum recommended sheave diameter. Yet so often we'll go into a facility and we'll see belts hung on a piece of 3/8 inch bar stock or round stock or 16 penny nail even. And I don't know too many belts that have a 1/8 inch bend radius. So we need to look at putting saddles on there or stretching them across 2 different hooks to kind of make sure that belt's not being creased at the cords. And remember, an under tension belt causes slip and generates heat. Heat kills belts. We're going to see that in just a second. The over tension belt overloads the bearing, increases heat. Heat kills belts. So over tensioning or under tensioning is going to kill your equipment in different ways. But the big thing both of those are going to do is cause high electrical consumption. So sheave diameter, impact on bearing and belt life. And this is one of those things I wanted to talk about. When we talk about these belts, doubling the load on a bearing, 1/8 the life. So it's a cubic law. It's 2 to the 3rd power. If we triple the load on a bearing at 1/27 the life, we can carry this out to wherever we want to go. We quadruple the load on a bearing, we 1/64 the life. So now we can start to see where we're getting an 11 to 22 year bearings only lasting 3 to 6 months. So one of the ways we can reduce load on that bearing is go to larger sheaves. Larger sheaves will allow us to reduce the heat and the stress on the belt. And we can lower our horsepower. The belt capacity works better. When we do that, we've got to pay attention to the feet per minute of our sheaves. We can overspeed sheaves especially on a 3,600 RPM machine. And one of the things we discuss in class is kind of the thought process behind there. Some math formulas on how to make sure you're not, but if you're using like Gates Design Flex Pro or Continental Make Power, it will tell you it's an unsafe configuration as you try to increase the size of those sheaves. And doing that, reducing that bearing load and reducing those temperatures results in a direct increase in your machine life, but it also lowers your electrical consumption. Pulley installation, and this is kind of generic pulley installation. But what we need to do is we need to have all the surfaces clean. And that's kind of the first mistake I see. Instead of cleaning those surfaces, we just slab them with anti-seize, so hopefully it'll come off the next time. Then we're going to verify the fit in the key, that tapered hub or that bushing needs to have an 80% contact. The key length needs to not fill the keyway completely, but to fill the keyway completely correctly, right? So that's that A plus B divided by 2 times 0.95. The insert, so we're going to make sure that we put that hub into the pulley in such a way that The install holes are lined up with the install holes, and the removal holes are lined up with the blank space on the pulley. Anti-seize is the enemy. We've already talked about that. And then we want to position that pulley as close to that driven end as we can, as close to that bearing as we can. And the example I use in class is I'll have the guy that goes to the gym every day after work. I'll have him stand up. I usually give him a gallon jug or a 2-liter pop bottle or something to hold out in front of him. And I'll let him just stand there as we talk through overhung loads. And after I notice that rotator cuff is starting to burn a little bit, I'll ask him if he'd like to move where he holds that to. And invariably, he'll bring that back in closer to his shoulder. And that's kind of how we drive home that, that weight hanging out at the end of that shaft is doing the same thing to your bearings that it's doing to that shoulder. Pulley alignment checks in a belt drive. So we can have a parallel or an angular gap. I will tell you that normally we have a little bit of both. And we can use a straight edge to get rid of that parallel gap or that angular gap, a horizontal angular gap. And we'll do it in class. We'll do it with a piece of string or a straight edge, or sometimes we'll let them use both, just depending on which one they're more familiar with. And we will get just an absolutely beautiful alignment. But what they'll miss is the vertical alignment between the two driver and driven. So then we'll kind of capture that back with the laser, and we'll talk about a belt hog. We use belt hogs in class. We use the belt alignment tool, the bat, if you're familiar with that one. And we'll use that to find the remaining parallel and horizontal angular, but you can also find the vertical angular with it. And then the big thing is, if it's a synchronous belt, watch where that shiv's running on the sprocket. When you start that belt up, if it's running down the center of that sprocket, it's probably pretty well aligned. But if it's off to one side or the other, that's telling you you've got some misalignment. Belt installation, this is another huge one that we see. Our mechanics do not want to slack the machines. They like to take and they cut the old belt off, or they roll it off using a screwdriver, and then they put the new one back on. So they'll take that belt, they'll put it over the small side, usually the driver pulley. They'll kind of hang it over that driven pulley. They'll put a screwdriver under it and they'll roll it over. That breaks and damages those tensile cords, and it also cuts that rubber coating. So this is our recommended procedure to prevent that. We need to reduce that center distance first. We need to slide that motor as close to that driven machine as we can. Then we need to put the belt on carefully. For a synchronous belt, we need to make sure the teeth are fitting in the grooves of both pulleys. For a V belt, we need to make sure that it's sitting in there correctly. That usually does it by itself. Then we start to extend that motor back away from that driven machine, whether it's stacked on top, side by side, whatever that may be. We start taking that up. And I can check my alignment with some of these alignment lasers while I'm doing that. So as I'm tensioning that belt, I'm setting my alignment to where I want it to be. Then I'm going to set my tension, and we're going to talk about some ways to set tension on the next slide, but that's going to be critical. And number 6, we're going to put the guards back on and run it, and we'll talk about some things we can do after we start running it. So you see up here, we've got 3 methods to tension a belt. And I want you to look at number 1, calibrated eyeball, where it says good, and understand that is not necessarily good. It's the bottom of the opportunities. So what I correlate this one to, and this is my little good, better, best, is when we used to go into Best Buy in the 90s and early 2000s and buy a TV. And you'd walk in, there'd be a guy in there in a blue shirt that said Best Buy. And you tell them you're there to buy a TV, and you say, do you want a good TV, a better TV, or the best TVs we sell? And they were laid out on the wall in that manner. And you go, oh, well, I want the best TV. You'd walk down to the best TV and be like, well, maybe I don't want the best TV. That's a little more than I wanted to spend. Let's look at those better TVs, right? So it's the same thing. Like, what are we going to do here? But with the calibrated eyeball, and this is what most of your folks are doing right now. This is what's happening in the field, most common. And they've all got away, well, if I can squish it an inch, if I can turn it 90 degrees, all these different methods to try to figure out belt tension. But the number 1 rule of the calibrated eyeball is when the time exists, tension the belt correctly. So if I'm going to go back and tension the belt correctly, I could just use a force deflection meter or force deflection meter and tension it correctly at that time. So that's going to go back to, and one of the things we're going to cover That's going to go back to following that manufacturer's data, but understanding that little card or the box that the belt comes in, and it gives you a belt tension. That gives you the belt tension for that belt at max horsepower, not necessarily the horsepower you're transmitting with the belt. Whereas Gates Design Flex Pro, Continental Make Power, all the industry or all the manufacturers in the industry have their own app that will tell you, hey, I have this size machine running this, this horsepower, this speed, this diameter of pulleys, this much centerline distance, and it will dictate the belt tension based on the horsepower that's being transmitted. So you're not overloading the bearings in that motor. So that is critical, and that's one of the things we're going to cover. And then, what do we do with that information? Do we have our mechanics look it up every time? No. We put it on a work order. We put it in that bill of work. So that the next time that belt gets worked on, we've got that information there, and we're not paying that mechanic to go look it up again. Then under there on the best is that sonic tester. It's the best in certain situations. So if you're in a situation where it's too noisy to use it, then that force deflection is better. So with these calibrated eyeballs, force deflection, sonic tester, there is an IR version of that sonic tester now that actually looks at the belt instead of listens to it. That I have not used personally, but that should help out in those noisy environments. But with those, that's kind of our limits for a synchronous belt. But when we get to a V belt, we get a really cool ability. We get the ability to check belt tension while it's running. We get the ability to do in-service belt tension checks to make sure we're not overloading our bearings, to make sure we're not wasting electricity, to make sure we're not damaging the belts and the pulleys with a strobe light. We can use that strobe light to calculate our theoretical RPM. Well, we're going to calculate our theoretical RPM based on the diameter of the driver driven. Once we have our theoretical RPM, we're going to get the speed of our driver, and we're going to compare it to the speed of our driven and compare all of that to the theoretical speed of the driven. And if we have 2% slip down to 0.5% slip, right, in a V-belt configuration, that's normal, and we're okay with that. At 4%, we're starting to cause damage to the belt. We're starting to cause damage to the pulleys, and we're wasting electricity, right? So we're slipping at a rate that we're wasting mechanical power that we've already paid for. At 6% slip, we're really, the tension factor has really gone down. And this is one of those things that at 6% slip, we're damaging machines, and going into some serious problems with our electricity consumption. So with a V belt, whatever your belt tension method is, I would put a PM into effect where I can adjust that on the fly, or I can check that on the fly. Belt storage practice, we already talked about.
Nathan, if you can hint to someone's asking the methods that you're showing with regarding V belt, do they apply equally to serpentine, or this is serpentine belts, or we should be treating
Matt,
them
are you
differently?
talking serpentine belts like in an automobile?
Yes, sir.
That's a great question. I've never worked the slip on the front end of my truck. Certainly a synchronous belt, it's not going to apply to. That should be 1-to-1. I would have to research that, Matt. I don't deal with enough serpentine belts in industry that I could look into that. I will make sure we get you an answer on the belt slip via serpentine belts. I would think those should probably slip a little bit. That's part of the safety factor of them, to make sure they're not taking out other equipment. But I don't know if the 2% number is the same. So I'll have to follow up with that one.
Thank you.
Yep. So belt storage best practices, we kind of talked about this. We want to be less than that 85, less than that 70% relative humidity, no direct sunlight, get them out of the windows. Talked about the saddle diameter. And one of the ways we can increase that saddle diameter very easy, go get a piece of 6-inch PVC pipe and cut it the length of that rod that you're already hanging those belts on, and just put that PVC pipe over that rod. Now you have a 6-inch bin diameter. And so that can kind of help save your belts without spending a whole bunch of money in your storeroom. Things to avoid: no bins smaller than minimum recommended sheave diameter, no back bins less than 1.3 times the minimum sheave diameter, and then don't stack them so tight that you fit too many in there and they start crushing each other. All right. So precision precision shaft alignment. This is when, and this is very eye-opening in class, we're trying to get the center line of two shafts located together when viewed from any angle during normal operating conditions. So whenever we do a rough-in inspection or a rough-in alignment with a straight edge or something like that, we're aligning the outside of the couplings. And when we align the outside of the couplings, it causes a little bit of problems because those couplings aren't always true. They've got some run out to them. So we use a laser, reverse dials to try to align the center of the shafts, and that's going to protect our bearings a little better. We've got to align it cold in such a way that we account for that thermal growth. And once again, there's kind of two types of alignment. We've got angular misalignment and parallel misalignment, just like we did in belt drive. So with that, we're going to find that most have a little bit of both, and they're going to have it in both directions, both vertical and horizontal. So we'll talk about some shaft alignment. So step one, we're going to have same pre-alignment checks, right? So we've got to get all this stuff, these assembly errors corrected before we go too far down the alignment process, or else we just start going that back and forth game that we talked about before. So we need to get that short leg removed. We need to get all that squishy foot removed. That's all that extra debris that's under there, the extra shims. Get them less than 4. Check the coupling. Do we have the correct key length? Do we have the couplings oriented to each other correctly? Do we have a correct gap between the coupling? We can check our bearing condition by doing a lift check and a run out check. Before we shut a machine down that's running, if we're going to work on something that's already in operation, we should take a set of as found readings. They're the baseline that prove what we did mattered. And they also are how we can prove that we've lowered electrical consumption. And then once we get that alignment process started, we're going to stop when we're within about 10 mils of the feet being where they're finally going to rest. And that's when we'll correct the angular soft foot. So a rough-in alignment, there is a rise over run method where we can measure the gap and figure out the rise over run. And you can see that on the left-hand side of your screen there. Oftentimes, when we do a rough-in alignment, we're just kind of guessing at the shim adjustment. Your mechanics are pretty good at figuring out what needs to be in there and getting the right amount in there. Parallel offset, we can correct by lifting that machine up as a whole or sliding it left or right as a whole, whereas that angular, we're adjusting the angle it's sitting at. And the whole goal of the rough-in is, one, to get the machine into a better state if we're not going to do a precision alignment for whatever reason. And two, it allows the laser or the reverse dials to work correctly. So if we're not roughed in, then when we take those readings on those reverse dials or those lasers, they're so far out that we get an error from the laser alignment. So precision alignment methods, the two we talk about the most in class are the reverse dial method. That's the one we'll do in class. And that's really still a great method. A little bit of graph paper and a reverse dial worksheet. And for a $1,500 tool, which is what a set of Starrett reverse dials costs right now, I can do the same thing that laser alignment system does. And in fact, I can do more than some of the cheap laser alignment systems do. So we'll talk about both of them and kind of where the best method is. I certainly like the laser alignment systems, but if I'm coming out of an outage and the entire world's waiting on a laser alignment system, knowing how to do the reverse dial is pretty handy. Same thing applies to both methods. We've got to correct the vertical and then the horizontal. And every time we move that machine, we have to remeasure. Our alignment tolerances by shaft speed, these are very common. These are at the coupling. This is what your laser alignment tool probably tells you to align to. And in class, we talk about, we're going to cross out acceptable and we're going to shoot for excellence. But also, if you look at that bottom general rule, for a machine that's less than 2,000 RPM, if we get every measured location, which means all 4 feet and the reverse dials that are mounted to the shaft, if we get all 4 of those within 0.02 of an inch of the cold alignment line, or for a machine greater than 2,000 RPM, we want to get them within 1,000th of an inch, we will have a much better alignment. So the Alignment tolerances you see in that chart are basically at the coupling, but they don't take into account the radial internal clearance left in the bearing. So as a general rule, we're going to try to get anything less than 2,000 RPM within 2,000ths on the same side of the cold alignment line, and greater than 2,000 RPM, we're going to try to get to within 1,000 on the same side of the cold alignment line. Optimum move. This is one of those beautiful things about that reverse dial is when I use the optimum move, I can sometimes make a better move than what the laser shows me. And once I plot this machine out, as you can see, the steps on here, then I can look at my 4 optimum moves and I can figure out the one that makes the most sense for my unique situation. Thermal growth. Methods to measure thermal growth are on the left-hand side. We've got permaline, dot bars, AccuLine, all sorts of optical and laser alignment systems, and they're either expensive, they take a lot of skilled interpretation, or a combination there of the two. Whereas I can take my spot radiometer or my temp gun, as you see in the picture on that slide, I can calculate my expected thermal growth using the actual temperatures that my machine runs at and compare it to the temperatures that it's going to be at when I align it. And I can calculate based on the coefficient of expansion of that material exactly how much that machine's going to grow. And then I can offset my machine cold so that it grows into thermal alignment. Documentation. When we are documenting stuff, it becomes critical that we document it and turn it in, and that gets turned into somebody who does something with it, right? So vibration, we're looking for less than 0.05 inches per second root mean squared. For bearing temperature, we're looking for less than 130 degrees. Coupling temperature, the cooler we can get it is better. The RPM, we're looking for it to be as required and to bring our amp draw down to get that RPM to where we want it. And that amp reduction is the first time that we can prove what we did mattered. That's the first time we can prove cost savings. Precision alignment, common errors and fixes. If your readings are changing every time you move them, you need to look at loose dials, loose lasers, loose coupling. Something is wrong in our setup. Our feet aren't tightened down, and so we should check all that. If the machine shifts after tightening, that can be due to some unresolved soft foot, some pipe strain, some lack of torquing, all those. And so we need to look into that. And if you just cannot reach your tolerances at all, that's when we start looking at, okay, what are my base? What are my feet? What's the hardware? Did I change all my hardware? What's the corrosion level on my base? So with that said, I'm going to kind of cover, these are the big ones, the takeaways. This is what we've got to have from this 1 hour that I've been here. So one, we got to get all the assembly errors corrected before we can attempt a precision alignment. 2, we need to replace all belts as a full set, not one-offs. Taper locks, no anti-seize or lubricant on taper locks. Belt tension, measure it by force deflection or the sonic method, not calibrated eyeball alone. But if it's a V-belt, the belt slip formula is an excellent way to check while it's running. Number 5, thermal growth is real. We've all aligned a machine where we started it up and it sounded great. And then as soon as we walked away from it, 6 hours later, it sounded like it's coming apart at the teeth. That's thermal growth. And then number 6, document as found and as left. We have to prove that our machines are getting better. More importantly, we have to be honest with ourselves about what we're doing and that our machines are working the way that we intend them to do. And not hiding our mistakes. Let's face our mistakes, put them on documentation so that we can hold ourselves accountable. And with that, I'll turn it back over to Michael a minute late.
Thank you. Yeah, it's always difficult. As I said, there's always a lot of material. It's hard to get it all in 1 hour. Yep. I know some of you guys had to leave. First off, thank you very much, everyone, for participating, for joining. I hope you liked it. I hope there was a lot of insightful information, gives you some ideas of where you are today, what maybe you're lacking, what the next steps might be for you. So this is really an extract of our courses. These are multiple day trainings that we offer, and we do the theoretical, which is what we can do through a webinar, basically like this. But then we also do the practical aspect. So we get the so experience and expertise with your own machines or with ours in our classroom. I know a lot of you guys are asking, can we get the presentation? So to answer the question for everyone right now, everyone is going to get the recordings, not necessarily the deck slide, but the recording of this webinar will be available to you, so you can review it, go back over some of the information, share it with your colleagues, your friends, and I hope that will help. So.